Hi friends, welcome back to the channel. So in this video we will be doing a couple of solved examples from the topic of thin pressure vessels. This topic is of huge importance once you start your career as an engineer. If you ask most of the practicing engineers, they usually come across a lot of thin walled structures. Let it be pressure vessels, let it be the propellant tanks of a rocket, to name a few. So there are a lot of structures which falls into the category of thin walled pressure vessels. So let's start with a very simple example, but definitely this will also open up a bunch of concepts. Okay, so as I usually say, please pause this video, try to read the question, try to do it on your own, and if you are not able to do it, come back and watch rest of the video. So let's get started solving this problem. Here in this case, we have a pipeline and water is flowing through it under a gauge pressure of 250 psi. Don't worry about the units, it's pounds per square inch. And the inner diameter of this particular pipeline is 12 inches and wall thickness is 0.25 inches. The first check that you should do is whether it falls to the category of a thin walled pressure vessel. So, in order to determine that, you simply compute the R by T ratio, and in this case, R by T ratio will come around 12 divided by 0.25, which will be 48. This definitely falls to the category of a thin walled pressure vessel, because usually it's not a hard and stringy formula, but if R by T ratio is greater than or equal to 10 or 12.5, then we can go ahead and call this pressure vessel or assume this pressure vessel as a thin walled pressure vessel and go ahead with the computations. Now they are asking us to find out what is the longitudinal and hoop stress developed in the wall of the pipe. So I think you take 10 mechanical engineers, 8 out of the 10 will know this famous formula for the hoop or the circumferential stress. Similarly, the formula for the meridional or the longitudinal stress. So just to make it clear, meridional and longitudinal are the same stress. I may use these two words interchangeably, but they mean the same. Here also circumferential and hoop means the same. Okay, so these are well-known formula. I would like to call them the most abused formula, because mostly people use these equations without knowing what are the assumptions that are built into it. Okay, in this case, can we go ahead and use this two formula? Think for a moment and come back. See, in this kind of a scenario where you have open ends, the meridional stress or the longitudinal stress will be 0, because this particular system is not having any closed caps. Okay, but there will be hoop stresses or circumferential stresses will be there, which will be or which can be obtained by using this particular formula. Now if you may be wondering why there is no meridional stresses or longitudinal stresses in this particular structure. See, the answer goes like this. If you really paid attention to the derivation of the formula, how we used to derive that formula? We used to take a pressure vessel like this, let's say a cylindrical pressure vessel with closed ends. In this case, I have made the ends spherical in shape, but doesn't matter. We can go ahead and try to derive the formula once again for the meridional stress. In this case, I'm taking this chunk of the structure or this portion of the structure and I'm drawing its free body diagram. Now what happens? There is an internal pressure which is acting like this, and then this is shown this using this light color, and then the red light color denotes the meridional stress that is acting in the structure. Make sense? Apologies for my poor drawing, but if you look at the same structure in 3D, it will look something like this. Okay, the key takeaway is that once we use the balance of forces acting on this particular structure, once you write down the equations, then it will look like this. Sigma L is a longitudinal stress, and the area over which it is acting can be written like this: 2 pi r times the T, where T is the thickness of the wall and R is the radius, times P. P is the internal pressure of the fluid that is inside this tank, times pi r square, which will be the cross-sectional area. The key takeaway is that this force, the force due to the internal pressure, is not acting here. It is not acting here. It can act here. This is a void space. There is no structure here. So actually this particular force, P pi r square, is actually acting over here, over this curved surface, which closes your pressure vessel. Okay, so since you had a closure for your pressure vessel, or since you had a closed end, that's why this term is arising, or that's why this term is coming into the equation. Now think of a case if you have a pressure vessel that is not having a closed end, simply it is having an open end. Then what happens? There is no force in the longitudinal direction due to the internal pressure, which in turn means that there won't be any longitudinal stress. Make sense? Simple, right? So to sum up things, when you have open ends, there will be no longitudinal stress, but there will be meridional stress. Sorry, there won't be any longitudinal stress, but there will be circumferential stress, which is given by this particular formula, PR by T. This formula holds true because your pressure vessel is a thin pressure vessel, thin wall pressure vessel, where R by T ratio is around the order of 40. Make sense? So rest of the things are simply plug and check. All quantities are given to you. The internal pressure, the radius of the line, thickness of the line, everything is given. So simply you can plug in all these values and get the circumferential stress. Now think of another scenario. Let's say I had some kind of a wall in my, let's say I have a wall over here. This is the wall denoted as capital A. Now what I am doing is I'm going to close the wall. So what happens due to some kind of a effect, the pressure inside the tank is going up by 3. It was initially 250 psi. Now it increases to a value of 300 psi. Now determine what will be the longitudinal and Hope stress developed in the wall of the pipe. See, in this case what happens, since the wall is closed, there will be a net external force acting in the longitudinal direction due to the internal pressure. Okay, so that will lead to the longitudinal stresses, which is again given by the formula PR by T. Make sense? So when the wall is closed, you will have both longitudinal and Hope stresses. Make sense? Now there is another hidden assumption here. There are two supports over here. You need to assume that these two supports are not providing any kind of a horizontal reaction force to the pipeline, because if the supports are providing some kind of a horizontal reaction force onto the structure, then also it may result, or it may cause some kind of a longitudinal stress in the pipeline. So the assumption that supports only exert vertical forces on the pipe hole should be there, that assumption should be there in order to precisely predict the longitudinal and hoop stresses in the pipeline. So to summarize, if you have open ends, there will be only hoop stresses. If your pipeline has got a closed end, then there will be both stresses, both longitudinal and hoop stress. And we are using an assumption that this supports only exert vertical forces on the pipe. Make sense? Thanks for watching.